Alright, the problem that I'm going to be going over with you is problem 6.35 from chapter 6. On 6.35, this problem is a question that requires you to use an equation that you get from the actual chapter. So on 6.35, hang on a second, I think I have a glare issue. Give me a moment. Alright, there we go. So 6.35, the equation that they tell you to grab is 6.5 from the chapter, and that would be E equals negative 2.18 times 10 to the negative 18th joules times 1 over n squared. And that gives you the energy when you're at a specific quantum energy level in an atom. So in the question, they tell you that the second energy level that you are at, that this atom, let me read the question one more time so I can make sure I'm telling you, it's going from N2 to N6. So for the first energy level that we're talking about here, its energy level, let's just write 2 here, that way we remember it's the energy level 2. It's negative 2.18 times 10 to the negative 18th joules. And then you're going to plug in 2 there. So that's the same as multiplying it by 1 over 2 squared, and I know 2 squared, that's 4. So it's this number divided by 4, and then you're actually able to figure out the energy of an electron at that level. So it's negative 5.45 times 10 to the negative 19th joules. Alright, that's the first step. The second energy level is energy level 6. So it's the same step as the previous one. We're using the same equation. But this time we're multiplying it by 1 over 6 squared, which is of course 36. And when we do the math for this one, we end up with negative 6.06 times 10 to the negative 20th joules. So now I have my two energy levels. And to figure out the change in energy for when the electron goes from 6 to 2, I'm going to take the difference between E6 and E2 to figure out how much energy is emitted. So I'm just basically subtracting these two numbers. So it's going to be the negative 6.06 times 10 to the negative 20th, subtracting negative 5.45 times 10 to the negative 19th. And don't forget your answer is going to end up in joules. I should have written a joules there, should have written a joules there. But in any case, I get my answer, which is 4.84 times 10 to the negative 19th joules. That's my change in energy. So now the question, I believe, is asking after that, let me look at it. The question is asking for, is this line in the visible region of the electromagnetic spectrum? So to figure out whether something's visible in the electromagnetic spectrum, we look at the electromagnetic spectrum in terms of wavelength. So we need to convert this into wavelength. Don't forget the equation E equals h nu. Now there's something that might save us a lot of time. We can actually translate this equation if we remember that there's the speed of light is equal to the frequency times the wavelength. What we can do is we can actually substitute in this equation for that one. So what it ends up being is you end up having delta E equaling the Planck's constant with, now let me rearrange this equation. It's going to be frequency equals c divided by lambda. So it's going to be c over lambda. And I have to get lambda by itself, so I need to multiply by lambda on both sides. Now I need to move delta E to the other side, so let me divide by the E on both sides. And it's going to be lambda equals hc divided by delta E. Alright, so now I know what I need to plug in here. So lambda is going to equal 6.626 times 10 to the negative 34th joule seconds times the specific, or the speed of light, which is 3 times 10 to the 8th meters per second, divided by the energy in this problem. Well, what's the energy? It's this up here. So I'm going to divide it by 4.84 times 10 to the negative 19th joules. This is going to end up giving me meters, which I'm going to have to translate to nanometers. So when I translate this, when I do the calculation, I end up with 4.10 times 10 to the negative 7 meters. So again, change it to nanometers. And we end up with 410 nanometers. This 410 nanometers is within the visible spectrum. We can see all light between 400 and 700 nanometers. So if we see it, this is at the end of Roy G. Biv, it would look violet, and that's the color. If you have any other questions on this problem, please see me in tutoring.